Okay, so we're going to do a couple of examples of kinematics problems where there are multiple accelerations going on, where the object has one acceleration, then another acceleration, and then possibly a third. And what we're going to illustrate here is that you need to examine each segment of the motion independently, because our equations for kinematics only work when the acceleration is constant. So what we're going to do is examine this first scenario. So in our first scenario, we have an object is moving east at 3 meters per second. So here's my object, and it's moving east at 3 meters per second. And it speeds up to 15 meters per second east. So it's going to be going at 15 meters per second east. Now, we're going to assume that there was a steady acceleration here, right? And this happens at a time of 2 seconds from the start, right? So we'll say T naught is 0, and I'll call this T1 is 2 seconds. And this is going to be our starting velocity and our second velocity. Then the object slows down at a constant rate of 1.5 meters per second squared until it comes to a stop. So over here somewhere, notice we're never told the object changes direction or anything. It just keeps going east. It slows down, it comes to a stop. So the speed here is 0. And so there's a bunch of questions here, and we'll probably answer those in the course of analyzing the motion. But what I like to do is just sort of find out everything I can about this, right? See what things are obvious, see what things aren't so obvious, and calculate whatever we can calculate. So what I can tell first is that since we sped up here, that must mean we had an acceleration in this direction. Okay, and I'm going to call this acceleration 1. And then here I slowed down, so I had to have had an acceleration in this direction. And it actually tells me that the acceleration for this amount, or for this segment, is 1.5 meter per second squared. And if our initial velocity was to the east, our velocities are all to the east, then this acceleration is to the east and this acceleration is to the west. So there might be some things that start jumping out at you right away. You may right away understand how much time must have passed here, right? You might also note that you can calculate the average speed for this interval or for this interval, right? And those things are definitely useful, right? And I would encourage you to find out as many things as you can and not really even worry so much about the questions at this point, especially when you're practicing, right? You're probably gonna answer the questions in the course of finding all the stuff you want to find anyway. So for me, one of the things that I like to do right away is calculate average speeds whenever I can. So I can see that the average speed for this interval, I can say V average is V1 plus V2 over 2. And so my average speed for this interval is going to be 3 plus 15, which is 18 divided by 2, so we're going to have 9 meters per second. And our average speed for this segment is going to be 7.5 meters per second. All right. So I know that I traveled at 9 meters per second, an average of 9 meters per second for 2 seconds there. So the distance for this first interval, right, the distance for the first segment, I'm going to call that distance 1, and we'll call the distance for the second segment distance 2. So I know that since V average is equal to D over T, I know that 9 meters per second equals D over 2 seconds. So we've got 18 meters of travel for this first segment. Now for the second segment, there are a number of different things I could do, but you'll note that I don't know anything about the time there. So if I want to do a calculation involving time, I'm going to have to first figure out what the time is. Or I can do something else. Perhaps I could use the timeless equation here, right? And directly get distance using the timeless equation, because I do have initial and final speeds and acceleration. Now, if I'm going to use the timeless equation here, you're going to have to be careful, right? So Vx squared equals Vx naught squared plus 2a. Kind of messy. Just give me a second. Getting used to writing it this way. So x squared x naught squared plus a delta x. So delta x squared minus x naught squared divided by 2a. So that's going to be 0 minus 15 meter per second squared. Up. Squared over 2 times 1.5 meter per second squared. Okay, so you'll notice right away that there's a negative sign here, and this is outside of this squaring. So this is going to give us a negative answer for delta x, but our change in position is clearly to the east. So we have to reconcile this. Well, notice that since this acceleration is pointing in what we're calling the negative direction, we got to put a negative sign here. And this will, in fact, take care of our problem with the negative sign. So we'll have displacement in the positive direction. So I have 15 squared divided by 3. So that's 75 meters. So we traveled a total distance of 18 plus 75 meters, or 93 meters. So the next question here is the distance the same as the magnitude of the object's displacement? And the answer, in fact, would be yes, because the object never changed direction, right? So what was the object's direction and rate of acceleration for the first 2 seconds? Well, we didn't find that. We can find it, right? So the acceleration would be equal to the change in speed divided by, or the change in velocity divided by the change in time. So final velocity, 15 meter per second, minus the initial velocity, 3 meters per second, over t, 2 seconds, right? So 15 minus 3 would be 12, divided by 2, 6 meter per second squared. Total amount of time for the object's trip. Okay, so we want to know then the time between here and here. Well, again, there's several ways to do that. The acceleration formula gives us a nice way to do it. Delta V over T. And it should actually be kind of obvious what it is, because right, our acceleration, delta V over T, so T equals delta V over A. So our change in velocity is minus 15 meters per second over negative 1.5 meter per second squared for a time of 10 seconds. So our total time of motion is, in fact, 12 seconds. All right, so let's see. For each interval, we have the starting and ending speeds, we have the accelerations, we have the time, and we have the distance. So we know everything about both of these motions. Let's look at another problem. All right, so our object begins from rest and accelerates north over a distance of 40 meters. So ignore this piece right here. 40 meters for a period of 8 seconds. The object then maintains a constant velocity for 15 seconds, after which it begins accelerating south at a rate of 5 meters per second squared for 6 seconds. Okay, the only two questions here: total distance traveled, and how far is the object from its starting point at the end of its series of motions. So there's kind of a lot going on here, right? So first, we begin from rest and we accelerate north. So our starting speed is 0, and we accelerate north for a distance of 40 meters. And this is going to become a problem really fast. So let's start here. Our speed is 0. We accelerate north. We travel 40 meters. In 8 seconds. So the time at which we're here is 8 seconds. Then we're going to go at a constant velocity for 15 seconds. So the time for this interval, 15 seconds. And then the object is still going to be going north, but it's going to start slowing down, right? And we're going to accelerate this way at 6 meters per second, 5 meters per second squared for 6 seconds. All right, so here's what we're going to do, right? We're going to organize this into 3 different segments of motion, right? So for segment number 1, our initial velocity is 0, and we travel a distance, delta x is plus 40 meters, and this happens in t equals 8 seconds. Right. So what can we do with that? Right. What can we do with this? Well, we can calculate what the average speed is. The average speed is 40 meters over 8 seconds, or 5 meters per second. Now, if the starting speed is 0 and the average speed is 5, that must mean our final speed is 10, right? Since V average equals, let's say, delta x over t, and then V average is equal to V1 plus V2 over 2, right? So following that line of reasoning, the average speed, 40 over 8, is 5. And if our average speed is 5, and our starting speed is 0, then our final speed must be 10. All right, so for the first segment, we traveled a distance of 40 meters. We have a final speed of 10 meters per second. So the speed here, when we get to this point, is 10 meters per second. I'm not sure what the rate of acceleration is there. We can calculate it. We know the change in speed is from 0 to 10, and that happens in 8 seconds. So acceleration, change in speed over t. So we gain 10 meters per second of speed in 8 seconds. And I believe that's 1.25 meter per second squared. Now, note this is not the only way to have done this. You could have used the position equation, right? X equals x naught plus v x naught t plus half a x t squared. These guys would be 0. And we would have said acceleration equals 2x over t squared. And this would have gotten you 1.25 meter per second squared, which you could have then used to calculate that the final speed was 10 meters per second. Okay, so our first distance 1, is 40 meters. And the position at the end of the first motion is plus 40 meters. Okay. So let's keep track of all of our overall information over here. And we'll do our work over here. So we have distance 1, 40 meters, change in position 1. So the position at the end of 40 meters, the end of the first motion is plus 40 meters. Okay, so now for our second motion, the object is going at a constant velocity for 15 seconds. So that means that the average is whatever the speed was at the end of the first interval, right? We found that that was 10 meters per second. Now, since it's a constant velocity, we know that the initial, final, and average speeds are all the same. So initial speed 10, final speed 10, average speed 10, and it does this for a period of 15 seconds, right? So it's got a velocity of plus 10 meters per second for 15 seconds. So we're going to multiply the velocity and the time, and that means we're going to be 150 meters in the positive direction. Notice we never change directions, we're just maintaining a constant velocity. So the distance traveled for segment 2 is 150 meters, and our position relative to the start at the end of this, right, we changed the position by 150 meters. So plus 150 meters. So our position at the end of segment 2 is going to be 150 plus 40, which is plus 190 meters from where we started. All right, so now segment 3. All right, so for segment 3, the object maintains a constant velocity, it begins accelerating south at a rate of 5 meters per second squared for 6 seconds. Okay. So our initial velocity is 10 meters per second. Our acceleration is south, so -5 meters per second squared, and the time for this interval is 6 seconds. So note what's going to happen here, right? This object that's traveling north is going to slow down, right? And it's actually going to stop and turn around. Well, how do I know that, right? How do I know that it's going to stop and turn around? Well, if we accelerate at 5 meters per second squared and our initial velocity is 10, it's only going to take 2 seconds for it to stop, right? And then we're going to be accelerating for an additional 4 seconds. So if we want to know what the final velocity is, Vx equals Vx naught plus axt. So that's going to be 10 meters per second. And of course, some of you could do this in your heads, right? You already know that it's going to be, you already know what it's going to be, because you know that we're accelerating at a rate of 5 for 4 seconds in the other direction. So 10, this is -30, so -20 meters per second. All right, so if you want to calculate the distance traveled, this is going to be tricky because we need to calculate the distance that it traveled before it stopped, and then the distance it traveled after it stopped. Because if you use the position function, you have to notice that this position function is not going to give you the distance traveled. It just gives you the change in position, right? So if I want to know the position at the end of the motion, x3, I can put in the initial position is 0, right? And then this will just give you the change in position for this third motion. Alternatively, I could put in the position at the end of motion 2, and then this would tell me what the position is at the end of the whole series of 3 motions, right? So that's actually kind of cool, right? Let's go ahead and do it that way. So 190 plus Vx naught, which is 10 times 6 seconds plus 1/2 -5 times 6 seconds squared. And this right here, this calculation is actually going to give me the final position of the object relative to the starting point. So evaluating the last part, 36 times -5 times 0.5 plus 60 plus 190 gives us a final position of positive 160 meters. So the final position, x3, is 160 meters. And if we had just evaluated this part, if we'd have made this initial 0, then we would have been told, okay, well, we're 30 meters south of where that third motion started, right? So that would have been, this segment is -30 meters. Okay, so this is the answer to the last question, right? our final position is plus 160 meters, and that is how far we are from where we started, but it is not the answer to the total distance traveled, right? To get the total distance traveled here, we'd have to figure out how far we went before we stopped, and then how far we went after we stopped. And to do that, we're going to have to break this down into two separate calculations. Okay. So we'll consider first the part before we stop. So we have our initial velocity is 10 meters per second. And we'll say that the final velocity is 0. And the acceleration, -5. We could also note from before, right? We noticed that, or maybe you didn't notice, but I did, that it actually took 2 seconds for it to stop. So if we want to do this, we have actually a quick way to do this, because the average speed is 5 and the time is 2. So the distance traveled is 10 meters. Okay. So then, distance, let's call this distance 3A, would be 10 meters. Then, after it stopped, it started going the other direction, and we know it did that for 4 seconds. We know the initial speed is 0, and the final speed in the other direction is going to be 20 meters per second. And so the average speed there is 10 meters per second. And so the distance traveled, if it's an average speed of 10 for 4 seconds, that's going to be 40 meters. So distance 3B, 40 meters. Okay, so the total distance traveled here is going to be 40 plus 150, which is 190, plus another 50. So 190 plus 50 is going to be 240 meters. Okay, so I'm going to go into the graphing part in the next set of lessons, and then you'll see that it actually would have been far easier to do all this if we had just graphed it right from the start. And it's a much easier way of interpreting these problems. Okay, so I hope this has given you a little bit of practice and insight into how you approach some of these problems. But you notice that every time the acceleration changes, you have to start over with a new set of calculations, right? Obviously, your paper would be a lot neater than this. You can keep track of each segment a lot easier on one big piece of paper. I have to obviously write this on a limited space, but hopefully this has helped you out.